Welcome back to Calculus 2. This is section 1.2, the definite integral. We're going to begin with the definition of a definite integral. In making this definition, we will have various vocabulary terms to encounter. Let's get started. So here is the definition. We want to start with a function which is defined on an interval. Given that we have a valid function, we'll define the definite integral of that function over that interval to be given by this expression on the left-hand side. And the expression on the left-hand side is evaluated as a limit of a Riemann sum. This definite integral exists provided that the limit exists. And if the limit does exist, then we say that this function f is integrable. Good, so two things are being defined. The definite integral, that's this expression on the left, and then the notion of when a function is an integrable function. Nice. Let's take a closer look at the definite integral. Find its various pieces. This elongated s as a symbol is referred to as the integral symbol. Used as a definite integral, we read the integral symbol as the integral. Nice. Attached to this integral are values a and b. Let's focus on those next. Those values a and b are referred to as bounds of integration or limits of integration. So in this expression, there is a variable. The variable is x, and these bounds of integration are indicating bounds of the variable of integration x. Nice. When we write down a definite integral, we write down the definite integral of a function. The function that you're taking the definite integral of is referred to as the integrand. So f is the integrand. And then the final piece is the differential dx. And the differential dx is indicating the variable of integration. Since this is the differential for x, that's telling us that the variable of integration is x in this case. And as mentioned before, that differential is telling you the name of the variable, and the bounds are telling you the values for which that variable is taken. Very nice. So here's an assignment. Write the definite integral of the natural exponential as a function of theta over the interval 0 to pi. So this is an assignment to check whether you have digested the definition of a definite integral. Very good. All right, so we've made the definition of a definite integral, and we saw various vocabulary terms: integral function, limits, i.e. bounds of integration, the integrand, the variable of integration given by the differential. Okay, so we have this new notion of a definite integral. We're in section 1.2, thinking back to section 1.1. Let's relate the two ideas in section 1.1 and 1.2. And that's done in this next theorem that continuous functions are integrable. So let's step back into 1.1. In 1.1, we made a definition for the area under a curve. Note the sentence before that, let f be continuous. So here by definition, whenever you have a continuous function, happens to be non-negative, then this notion of the area under the curve is defined. How is it defined? It's defined as the limit of a Riemann sum. We set it equal to a on the right-hand side. Capital A is the limit of a Riemann sum. Okay, that's from section 1.1. Here in section 1.2, we're making the definition of a definite integral to be exactly the limit of a Riemann sum. The difference from 1.1 and 1.2 is that in 1.2, this definition of a definite integral, the function f is not necessarily continuous. But in 1.1, it was required to be continuous. And in that case, this right-hand side, was defined as the area under the curve, so that this limit does exist. Then by the definition of a definite integral, as this limit exists, that's showing you that the function f is integrable. Hence this theorem, if you have a continuous function, then you have area under its curve, and thus the function is integrable. Beautiful. Throughout the course, continuous functions are quote-unquote nice functions, important functions, useful functions. If you have a function which is continuous, you gain a lot. That cannot be overemphasized. All right. So we've had a nice theorem that continuous functions are integrable. In other words, the area under their curves are defined. They can be evaluated as finite values. So let's look at some examples of doing exactly that. Evaluating definite integrals using geometric formulas. So you want to think about rectangles, triangles. You know formulas for computing their areas. You also know how to compute the area of circles. And that's what we'll do next as an example. Okay, so here's an example. We have a definite integral, the elongated s, lower bound a equaling -5, upper bound b equaling 0, integrand as a radical function, and the variable of integration, x. Good. Let's focus on the integrand. Looking at the integrand, let's set the integrand equal to y. Let's make a note. If we look at this function, it is a radical function of a quadratic function. That's a composition of functions, which each is a continuous function, therefore the composition is continuous. Introducing the y, we can then square either side. On the left-hand side, squaring will get y squared. On the right-hand side, squaring will nicely remove the radical, allowing us to then collect all variables on one side. And this form, if it's not familiar, you want to pause the video and go investigate this equation. This is a circle of radius 5. So let's draw a circle. This one would happen to be centered at the origin. The key thing is that the radius is 5, since 5 squared is 25. All right, so if we take the center to be the origin of the xy plane, then x values would occur between -5 and +5. And then looking at the bounds of integration, we want x values taken from -5 to 0. Hence, I've indicated that of all of the area contained in this circle of radius 5, the only area that I'm concerned about in this definite integral is area occurring for x's between -5 and 0. And then for y values, I want y set equal to this radical term. And we know that a radical is always non-negative. Thus, x's will be between -5 and 0, and y's will be non-negative. In other words, we're getting a quarter circle. Well, use a geometric formula for the area of the entire circle. The area of the entire circle is pi r squared. This circle has r equaling 5, so that's 25 pi. But the definite integral represents only a quarter of the circle. Thus, we can easily evaluate this definite integral using a geometric formula as the value 25 pi, that's the total area, divided by 4. All right, so let's take a look at what we did. We have bounds, and we focused in on the integrand and thought about what is that integrand. And through arguments, we found that it's a portion of a circle. Excellent. All right. So this is a play on the example that we just looked at, but with variables a and b introduced. Don't confuse these with the bounds that we were looking at earlier. These are various values, a and b, variables. The b we're going to take to be positive so that we can move from a off to the right by an amount b to determine an interval of integration. And this function f is similar to the integrand we were looking at. Since there is a radical, a radius term squared minus x translated by a, quantity squared. Okay, I'm going to watch a little video here. So this quarter circle that we're looking at is similar to the example that we just had, but with the variables a and b, we can produce a nice little movie. So taking any of these quarter circles, if we freeze this video at any point, we would then have a definite circle with a definite area, definite radius. And then squaring that radius, multiplying by pi, gives you the area of the entire circle. Divide that by 4 to then get the shaded area. And the shaded area can be represented as a definite integral. Very good. Okay, so we have made a definition, introduced some vocabulary, had a nice theorem which ties in today's definition in section 1.2 with the definition of area under the curve from section 1.1. And we've done an example where we can, thanks to that continuity between 1.1 and 1.2, we can use geometric formulas to evaluate definite integrals. Very nice. Let's consider the relation between area and the definite integral, with the focus of coming to the notions of net signed area and total area. So here's an example. We're looking at a definite integral. The bounds of integration are -4 to 2. Our integrand f is a piecewise defined function, and the variable of integration is x. So x will have a value as small as -4 and as large as 2. The function f, however, is defined for all x's, but again, we only want to have x vary from -4 up to 2. So that's considering both negative and positive valued x's. Our piecewise defined function f is defined for negative values as this absolute, and for non-negative values as this expression. Okay. So note that the integrand is a continuous function, but that it's going to take negative values between -4 and 0. We would produce the graph of f in this fashion. You can confirm that by looking at the piecewise definition, that both pieces are given as manipulations of the absolute value graph. Taking x and adding 2 to it would horizontally translate the vertex of the absolute value graph from the origin to -2, 0. And then subtracting 2 from outputs of this absolute value would move that vertex from -2, 0 down to -2, -2. Likewise, on the second piece, subtracting 1 from x has the effect of horizontally translating the graph to the right by 1. So the vertex of the absolute value function at the origin is moved to 1, 0. Putting a minus on this absolute value function would then have the effect of taking the upward opening absolute value and have it downward opening. And then adding 1 vertically translates the vertex up by 1 to 1, 1. We have two triangles. One triangle is below the x-axis, one triangle is above the x-axis. We can use formulas from geometry to compute the areas enclosed. And the one that occurs below the x-axis, we'll assign that as a negative area. So let's do that for the larger triangle. The base is 4 and the height is 2. 2 times 4 is 8, divided by 2 gives you 4. So the larger triangle would have an area of -4. And the smaller triangle with base 2 and height 1 will have an area of 1. So let's mark those down. And then looking at the definite integral, you want to think of, well, what is the area between the curve and the x-axis? And that's these shaded areas. But one of the shaded areas is a negative value and the other positive. So we add those two together and then result in a value of -3. And then we term this the net signed area. So this definite integral, evaluating out to 3, is a net signed area of -3. By being negative, that's showing you that most of the curve is underneath the x-axis. So the negative portion, the positive portion gives you a net sign of -3. Good. If, on the other hand, we were to flip the negative portion and have it sit above the x-axis, In the definite integral, that can be accomplished quite easily by simply putting the absolutes around the integrand. Remember, the absolutes will return back only non-negative values. Then that negative 4 will turn into a positive 4, which is the absolute value of negative 4, and 4 plus 1 is 5. So by placing absolutes on the integrand, evaluating the definite integral, the value that you produce is termed the total area. Very nice. So that's two different types of areas, net signed and total area. Perfect. So area in the definite integral, we went over net signed and total area. Next, let's look at properties of the definite integral. You should recall that we did properties of summation notation in the previous video. All right, so we have the first property on the screen, and we have a little animation to watch. We have the value b moving away and towards a, and as you do that, the amount of shaded area under the curve changes. So what if we were to take the lower and upper bound to be exactly the same? Then that would leave no opportunity to shade area under the curve. Hence, the definite integral from a fixed value to the same fixed value is 0. Okay, so that's the first property. Second property is a definite integral from a to b, integrand f dx, is the same thing as the definite integral from b to a of that integrand if we place a minus in front. So let's understand why one has a minus in front and the other does not. And to understand this, we'll go back to the definition. So the definition of a definite integral is the limit of a Riemann sum. And the key part to understanding this property is in the delta x. All right, we recall exactly how delta x was defined. B minus a over n. In the previous video, we treated that as the length of the interval, where a was always smaller than b. But here in the definition of a definite integral, we simply refer to the a and the b as bounds of integration. So if we were to interchange the bounds of integration, if a were to become the upper bound and b were to become the lower bound, then using this definition, limit of a Riemann sum, delta x, how would we phrase out delta x on the right-hand side? We would use the upper bound a, subtract the lower bound b, and divide by n. And then how would these two delta x's relate to each other? They would equal each other if one is prepended by a minus sign. Hence, one side has a minus and the other does not. Very nice. So interchanging bounds introduces a minus sign out in front. And we will have many opportunities to make use of this property. Good. Third property. Left-hand side is the integral of a sum or difference. Right-hand side is the sum or difference of two separate definite integrals. This should be reminiscent of a property that we had before in section 1.1. Let's recall that property. It was a property for summation notation that we could essentially distribute the operation of summation to each sequence. So here in the property of definite integrals, that's essentially what we're doing. We're distributing the operation of integration to each integrand on the right-hand side. And that these two are related since the definition of a definite integral is the limit of a Riemann sum. Very nice. Next property. Next property is that a constant can pull through the definite integral. Let's look at this. You're going to be asked in an assignment to formally produce this argument. So on the left-hand side, we have the definite integral of a constant times an integrand f. If we use the definition of a definite integral as the limit of a Riemann sum, then our function f would have to be multiplied by c. And then if we go back to section 1.1, we could then use properties of summation to bring that constant c out into the front. And then we can use properties of limits to bring the c out in front of the limit. Very nice. Okay, so here is the next property. We are relating one definite integral to the sum of two definite integrals. You want to pay attention to the bounds of integration. On the left is the definite integral from an a to a b. And then on the right, we're taking the definite integral from a to c. And then again from c to b. So the integral from a to c would be the darkly shaded area, and the integral from c to b would be the lightly shaded area. This is on supposition that the c value is occurring somewhere between a and b. However, this statement does not rely on the c value being taken between a and b. The c value can occur outside of the interval a to b. Here the c value is to the right of b. On the left, the area that we want to consider is only between a and b, the lightly shaded area. Then going from a to c is producing too much area. But then from c to b, notice that the c value is larger, and it's being taken as the lower bound. Therefore, the natural order of the bounds is to go from b to c, which would require putting a minus sign. Thus, the amount that you go over in the interval a to c is taken away in the integral c to b. Let's watch the c move from outside of the region to the right, off to the left. And then again, consider here with c to the left of a, in the property on the left-hand side, the integral from a to b would be the lightly shaded area, is by this property set equal to a to c. Well, a is the larger value taken as the lower bound. Then the darkly shaded region would appear as a negative signed area. And then from c to b produces too much, but how much too much? Exactly the darkly shaded area. All right, so these are the properties of definite integrals that you want to have familiarity with. Very good. And then here is that assignment to formally go and establish this property. Go back to the definition of the area of a curve. That should then tell you that you're looking at the limit of a Riemann sum. A Riemann sum is a finite sum, and you have properties of summation that can be applied to pull the constant through. And then you have to go all the way back to first semester calculus and apply a property of limits. Very nice. Okay, so this is properties of definite integrals, and by the assignment, you will relate properties of definite integrals as being based on properties of summation and properties of limits. Another important idea that we go over in this course is comparing one thing with another thing. The properties was one thing exactly equals another form. Here in the comparison, one thing is less than another thing, or one thing is more than another thing. Let's take a look. All right, so we have three properties that we're going to discuss. Let's start with the top. If you take an integrand, which is non-negative, then its definite integral can be interpreted as the area under the curve, and the curve, by being non-negative, will produce a positive area. For the second property, if you have one integrand, which is bigger than a second integrand, always on some interval a to b, then the area under the larger integrand is going to be greater than the area under the smaller integrand. Very good. And this last one is a little bit more involved, but it's essentially the same as the previous. And this third one is going to be important to us later in the course. So let's use some care here. The assumption that we're making is that we have an integrand which is always bigger than some value, and an integrand which is always smaller than some other value on a given interval. So for the small value, I've chosen 1 and drawn that as a horizontal line over a interval 0 to 2. And then for the larger value m, I've chosen 2.5 as an example. And then I've drawn in the sketch of some function f of x, which has outputs that are always occurring between little m and capital M. Good. So using the second property that we had, this f is always bigger than little m, and this f is always smaller than capital M. Treat the little m and the capital M as functions. Then the areas that they define will bound the area produced by the f. But the areas produced by the little m and the capital M are rectangles, and we can use geometric formulas to compute their area. The height is m in both cases, and the base is b minus a. Thus, we get that on the left, it evaluates to little m times b minus a. On the right, capital M times binomial b minus a. Very good. So these are properties yet again, but they're not equalities, they're comparison properties. They involve inequalities. Fantastic. So we're in section 1.2. We've made a definition of a definite integral, and we have one nice application that we can do. The application is average value. Let's take a look. Let's go back and think of the simplest case of average value, and that might be one value and a second value, their average would occur directly in between. So how do we find that average value, which we have a notation of x bar? X bar can be computed by summing the two values and dividing by 2. This can be extrapolated out to an average value of n values by summing the n values and then dividing by that number n. For us, since we're going to be interested in deriving average value of a function, let's take these n values as function outputs. And I've used the notation xi star to be reminiscent of a Riemann sum. We'll come to that shortly. First, let's note that this numerator is a sum of n function outputs, and we can therefore use summation notation to write out the numerator as the sum of n function outputs. And then that numerator was divided by n, which is the same thing as multiplying by the reciprocal of n. So that is close to being a Riemann sum, but the Riemann sum requires not just the height, but the height multiplied by the base, in other words, delta x, and we're missing that delta x. But thankfully, there's a 1 over n out in front, and delta x is the same thing as b minus a multiplied by 1 over n, which means we can solve for 1 over n by dividing both sides by b minus a. So if we do that, we get that delta x over b minus a is equal to 1 over n. And delta x is a constant, b minus a is a constant. So that if we take 1 over n and replace it with delta x over b minus a, we can leave the 1 over b minus a in the front and push the constant delta x, thanks to properties of summation, push the delta x through the summation. Very nice. Then, voila, we are now looking at a Riemann sum multiplied by a constant. Fantastic. So we're going to take the definition of f_av, the average value, to be the limit as the n, the number of sampling points, goes out to infinity of this constant times a Riemann sum. Good. Let's manipulate this a little bit. Pull out our properties. So here let's use properties of limits. This 1 over b minus a is just a constant, and thanks to properties of limits, this constant 1 over b minus a can be brought to the front of the limit. So here's the limit, so we can interchange these two operations. Let's do that. So now the constant is brought out in front, and we'll first perform the operation of taking the limit. Oh, but this is exactly the limit of a Riemann sum. And we know from today's video that the limit of a Riemann sum, if it exists, can be identified as a definite integral. So doing that, we then come up with a definition for the average value of a function. If the function f is integrable, then we can compute the average value of the function over this interval a to b through this expression. 1 over the length of the interval times the integral of the function f. Beautiful. So here's a nice assignment. Compute the average value of f in 3 different cases. First case for the function x squared over the interval -1 to 1, and use that the definite integral from -1 to 1 of x squared is 2/3. Compute another average value, but for the function x cubed in the interval -2 to 2. Note that you're not given the definite integral over -2 to 2. Hint, sketch a graph. Think of properties of, think of the net signed area in f of x in number 2 and f of x in number 3. In number 3, you have sine of x over the interval 0 to 2 pi. Fantastic. That brings us to the end of section 1.2, the definite integral. Thank you very much for watching. See you on the next one.